Good morning, dear students. Uh, Department of ECE welcomes you to the lecture series on cryptography. The subject code 17EC744, 7th semester, module number 1, the lecture number 8, the last lecture under this module number 1. And this is compiled and presented by A.V. Kolki, Assistant Professor, Department of ECE, KLS PDIT, Hadiyar. The contents covered in previous lecture were polynomial arithmetic with coefficients in the field of ZP, and finding the GCD of the polynomials. So these are the contents were covered in the earlier lecture. The topics we are going to discuss under this lecture are the finite fields of the form Galois field 2 to the power of n, modular polynomial arithmetic, finding the multiplicative inverse. These are the contents we are going to discuss today. The main objective of this lecture, the students should be able to understand the concepts like the finite fields of the form Galois field of 2 to the power of n, modular polynomial arithmetic, and finding the multiplicative inverse values of a Galois field of 2 to the power of n here using a tabular method and as well as using an extended Euclidean algorithm. The finite fields of the form Galois field 2 to the power of n. The polynomials over p raised to n with n greater than 1 operations modulo p to the power of n do not produce a field. If a prime number and its power n, if you are taking with the modulo of p to the power of n, that do not produce the field. It means that the a1 to m7 axioms, whatever the polynomial we may be finding in this condition, that polynomials may not follow the axioms that are a1 to m7. So that is what it is mentioned. There are structures satisfies the axioms for a field in a set with p raised to n elements, where p we are considering as 2. The p value we are considering as 2, and that is what we are concentrating in this lecture, that is Galois field of 2 to the power of n, and this will be following or satisfying all the axioms of the field, that is a1 to m7. The main motivation for this finite fields of the form Galois field of 2 to the power of n is virtually all encryption algorithms. It may be a both symmetric and public key that we are discussing in the next lecture onwards, involve the arithmetic operations on integers with divisions. So that's why this is the main motivation for discussing the Galois field of 2 to the power of n. For efficiency, the integers that fit exactly into a given number of bits with no wasted bits pattern, integers with range from 0 to 2 to the power of n minus 1, fitting into an n bit word. So this is the way of we are not wasting a single bits in that. Without wasting, we need to have a range of the bits n bit word. So that's why we used to call, even in our computer machines, we say that 8-bit word, 8-bit computer, 12-bit operating system, sometimes even say that 32-bit and even 64-bit. So that's way we are computing here also the finite fields of the form of 2 to the power of n. It is ranging from 0 to 2 to the power of n minus 1. A modular polynomial arithmetic. Consider the set S of all polynomials of degree n minus 1 or less over the field z suffix phi. So with this field, thus each polynomial has the form of f of x is equal to a n minus 1 into x to the power of n minus 1 plus a n minus 2 x to the power of n minus 2 plus so on ai raised to a1 raised to x1 plus a naught is equal to. So this is what we can confine and we can put in the form as the summation of I equal to 0 to n minus 1 ai into x raised to I, where each ai takes on a value in the set that is ranging from 0 to p minus 1. The I is taking the value of set values or elements of the set are 0 to p minus 1. There are a total of p to the power of n different polynomials in such set S here. We'll take one example and we'll try to understand in better way. For example, if I take my p is equal to p value as 3 and n is equal to 2, and according to the equation of Galois field of 2 to the power of that's way. So like that, here my p is 3 is there and n is 2 is there. So therefore p to the power of n means 3 square. That's equal to, we supposed to get, there are uh, 9 polynomial sets with these p and n value. How do we get this, the 9 polynomials? So you can count down here. We are getting the first one, that is 0 1 2. So next x plus 1, x plus 2, 2x, 2x plus 1, 2x plus 2. How do we get this? It is mentioned here, that is n equal to 2 and p equal to 3 here. So p equal to 3 means we are having elements, the set elements as, that is 0 comma 1 comma 2. These are the set values. P equal to p of the set p of 0 to n minus 1, that is 3 minus 1. So therefore we are having how many elements in this set? We are having 3 elements in this set, that are 0, 1 and 2. And this n, it stands here, that is x raised to 0 and x raised to 1. So the n value, it is finding out the bits, number of bits, the 2 bits with the weightage, its weight as x to the power of 0, because it's a polynomial. So that's why I've taken that x here, x to the power of 0 and x to the power of 1, because 2 bit is there, n equal to 2 is there. So therefore 1 bit, 0th bit and first bit. Now I can write the combination of these values now. I can write the combination of this 0, 1, 2. How I can write the combination of that? 0, 0 I may write. That's equal to, I am getting as 0, as I got here 0 here. The next combination I may be having 0, 1, and its equivalent value will be, or polynomial will be, we can have x to the power of 0 means it's 1, so therefore I am writing here 1. Then 1, 0, 0, 0, 0, 1. Yeah. Then the next combination is 0, 2. Then the value of this is 2. Why I taken 0, 1 and 2 here? Because the elements present in the P set are, because P we are taken as 3 here. So therefore the set values will be 0, 1, 2. The combinations I have considered all the combinations with keeping x equal to 0 and x naught I have taken 0, 1, 2. So therefore I got this 0, 1, 2 values. These are the one set of polynomials. Then I need to increment this x raised to 1 now, because these are the maximum possible combinations here. So I had here, so next combinations will be, I starts with 1. I am setting x equal to x to the power of 1 as 1, and next again the combinations I am writing. Now what is the equivalent value of this in the form of polynomial? X to the power of 0 means it's 0, and next x to the power of 1 means it is x. It is x. So that's how I got the next polynomial equation. And after this, what is the combination? Next combination I can have 1, 1. How can I write this 1, 1 in the form of, in the polynomial form? This means, this 1 means it is the left, that is x, plus, and this is 1. It is in the this one, the bit x to the power of 0, x to the power of 0, and that is 1 means it is 1 value. So therefore we are getting that value as 1. The next combination is 1, next 2. And how I can write this? Again x plus, what is this? 2. X to the power of 0 into 2. The x to the power of 0 means 1, 1 into 2. We are getting the value of that is 2. So this is the another set here. So third combination what I can have? So 2 and 0. What is the answer for this? What polynomial I can derive from this? That is 2x. So that's how I got this. The next one. The what may be my next combination? 2, 1. 2, 1 means 2x plus 1. That is what I wrote here. After that, what is the last combinations? 2, 2's 2. So 2, 2 means 2x plus 2. So that's how we got these 9 polynomials for the condition p equal to 3 and n equal to 2. Similarly, you can try out this now. P equal to 2 and n equal to 3 is there here. So what are the polynomials? How many polynomials we can find here? 2 to the power of n. N is 3. P equal to 2. P to the power of n is there. And here we are having P means 2 and equal to 3 here. So therefore 2 to the power of 3. That is, we are supposed to get 8 different polynomials under for this given data. What are the possible the weights we are getting here, n equal to 3 is there this time here. So therefore we are having x to the power of 0, x to the power of 1 and x to the power of 2. And how many the p equal to 2 means we are having the set value of that is 0 p minus 1, 0 comma p minus 1. P minus 1 means it is 1. So these are the set values we can have it. So therefore altogether what are the combinations we may find here? I can start with 000 and I must end with what? What is the last combination I may be getting here? My last combination for this will be this. When all zeros is there, what value, what polynomial we get from that? We get the polynomial from that as 0. 0, 0, 1, it is 1. Then 0, 1, 0 means it is 1. 0, 0, 1, 0. What we get for this? 0, 1, 0 means I am getting the value of that is x. Then 0, 1, 1, that is x plus 1 I get it. So like that when I come to this 111 and that value will be, what is the corresponding weight for this? X square. What is the corresponding weight for this 1 here? For this corresponding 1 the weight is x square is there. For this corresponding 1 the weight is x raised to 1 and for this one the corresponding weight is x to the power of 0. X to the power of 0 means it's 1. So therefore we are getting the equation as x square plus x plus 1. So that's how we are finding the 8 polynomials according to this modular polynomial arithmetic. We can find like that. So we can compute a field of Galois field of 2 to the power of n. Just we have seen an example 2 to the power of n, that is 2 to the power of 3 we are discussed. So how can we compute that? So there are some instructions here we need to follow this in order to construct that. A polynomials with the coefficients of modulo 2 and these polynomials degree is less than n here. Whatever the polynomials we are getting, it should be a less than n degree. And these Galois field of 2 to the power n must reduce the modulo an irreducible polynomial of degree n. And such irreducible polynomial we are using for multiplications only. We are using an irreducible polynomial to simplify the multiplications. Whenever we find a multiplications, we are taking the help of an irreducible polynomial. We are taking the modulo of that to reduce in case of multiplication operation. Basically, what is an irreducible polynomial? An irreducible polynomial, that is, it is f of x over a field f, is called irreducible polynomial if and only if f of x cannot be expressed as a product of two polynomials both over f and both of the degrees lower than that of f of x. And further, an irreducible polynomial is also called as a prime polynomial. Whatever the polynomial is given to me, I need not to factorize that. It is not possible to factorize. So this is one way. Another way I can say that a polynomial is divisible by itself and 1. And that's why I said that in an irreducible polynomial may be a prime polynomial. What is prime here? A prime means it can be divisible, and that number can be divisible by itself or 1 here. Such number we call it as a prime. Similarly, the same condition holds good for this irreducible polynomial or a prime polynomial. Any given polynomial it can be divisible by itself or one such polynomial also we call it as an irreducible polynomial. And the next one is we can find a inverse. How we can find a inverse for a Galois field of 2 to the power of n? By using that table method. We are constructing overall our table over the field of 2 to the power of n, Galois field of 2 to the power of n, or else we can also use an extended Euclidean algorithm to find the inverse. Let us discuss that how computationals goes by constructing that table. So these are some of the brief the steps are mentioned. We need to follow this for addition, multiplications. Let us glance here. Since coefficients are 0 or 1, can represent any a polynomial as a bit string. That's using a combinations of 0, 1, we are having a polynomial string, bit string. Addition becomes a XOR of these bit strings. Whatever the bit strings we are having, in order to perform a addition of that means it is an XOR operation. Whereas for multiplication, we are doing the shift and XOR operation, and modulo reduction done by repeatedly substituting highest power with remainder of irreducible polynomial, or you can make use of shift and XOR. Let us discuss these things with an example in the next slide. In this example, we considered already an irreducible polynomial. We are considered an irreducible polynomial. What is the irreducible polynomial here? We are considered x cube plus x plus 1. I don't have any factors for this given polynomial. I cannot have a factorize. I cannot find out the factors for this. So that's why I say that this polynomial is an irreducible polynomial. It can be divisible by itself or 1. So that's why I'm saying it is irreducible polynomial of for a Galois field of 2 to the power of 3. In Galois field 2 to the power of 3, we have two equations, polynomials we can derive here. As I already mentioned you how to derive the 2 to the power of 3 here means we are finding 8 different polynomials, that is x square plus 1, and then another polynomial is x square plus x plus 1. So that's why we are getting the two polynomials over the Galois field of 2 to the power of 3. X square plus 1 means it is 101 in the form of binary, and x square plus x plus 1 is it means it is 111. So we perform the addition operation over this and we'll try to find out what answer we get it. And in just now I mentioned that is a XOR operation, and let us glance that how exactly this will be done here. X square plus 1 plus, because we are performing addition operation, this first polynomial plus second polynomial. When I add these two, that is, we said that it's a XOR operation. X square is XORed with x square. What I get? 0. 1 is XORed with 1. We get 0. What we left here? We left with x value. So that's how the addition will be performed. The same thing for simplicity, I have taken the same example for a binary value. 101 is XORed with 111. When I add these two, XOR these two values, I am going to get the answer for that as 010. 010 means what is the, how we are writing this in the polynomial now? It is x to the power of 0, x to the power of 1, x to the power of 2. So I left with x to the power of 1 into 1. I am getting that answer as x value. So that's how I got it. And for multiplication, the multiplication is multiplication is carried out x plus 1 plus x square plus 1. So I have considered the same polynomials. I have taken the another the example here, the x plus 1 into x plus x square plus 1. So these are the two polynomials I want to multiply it now. When I multiply these two polynomials, what is the result we get it? So when I multiply here, x into x square plus 1 plus 1 into x square plus 1. Then I am multiplying this x into x square plus 1. I am getting the answer for that as x cube plus x plus then this x square plus 1 into 1 means I am getting the answer for that as x square plus 1. So the total result is now x cube plus x square plus x plus 1. So this is what the answer what we are getting for these two product of these two polynomials. And now what I'm doing the shift and XOR operation. Why I'm shifting by one position here? I mentioned here shift towards the left side by 1. Why here 1 here? The 1 is mentioned because we are multiplying here the x square plus 1 by x here. So that's why I have taken here the shift by 1 position. So that's why when I shift by one position to the left hand side, I am going to get the answer for that as 1 0 1 0 1 0 1 0. I'll get it. And whereas for the second part, the 1 0 1, I am shifting it for 0th time because x to the power of 0 is 1 is there, x to the power of 0. So therefore I am shifting 0. I am shifting this data 101 data for 0 times towards the left hand side. So therefore the value of the 101 will not be get affected here because 0 time I am shifting it. Now you can perform the XOR operation between these two values. Perform the XOR. What is the answer? We get it. We get the answer for that as 4 ones. That is 1 1 1 1. So this is when I translate this value into a polynomial, I am going to get the answer for that as x cube plus x square plus x plus 1. So that's how I got this, the product of the two given polynomials. This is one way. Another way, with the help of an irreducible polynomial, how can I compute it? So that is the next concept for the multiplication. So here it is mentioned that the polynomial modulo reduction get q of x and r of x is, that is, x cube plus x square plus x plus 1. I got it. After multiplying the two polynomials, so here it is. What is my answer? X cube plus x square plus x plus 1, that I have taken, and that for that I am doing the mod operation of my irreducible polynomial. What is my irreducible polynomial here? X cube plus x plus 1. With that I am doing the performing the mod. So when I do this, what I get here? So how to simplify this? So let us take that now. X cube is there. I'll substitute the value of x cube by taking irreducible polynomial. What is the answer I get from the irreducible polynomial here? My irreducible polynomial is x cube plus x plus 1 equal to 0. This is what my irreducible polynomial. If I derive x cube is equal to what I get here, minus x minus 1. What is the additive inverse? The additive inverse will be a and minus a. For a, the additive inverse will be minus a. I am already having here minus a. What is the additive inverse for this? Its additive inverse will be x, and for minus 1, that is 1. By using the additive inverse property here, I got here x cube is equal to x plus 1. Substitute this value in the multiplied polynomial, that is this polynomial. Substitute the value of x cube in this. So what I get here? So when I substitute the value of x cube in this, I am getting that answer as x plus 1 plus x square plus x plus 1, and do the XOR operation for this now. If I do the XOR operation, x plus 1 will be cancels with this x plus 1, and we left with x square, and we left with x square. Answer for this, we left with the x square, that is this way. So this way, after multiplication, whatever the polynomial you are getting, you are reducing that polynomial by taking the mod of irreducible polynomial, and the answer will be, final answer will be now x square, and that is what it is mentioned over here. That is what the answer it is mentioned, that is 0 1 0 0. So this way, for the multiplication, under multiplication we are taking the help of an irreducible polynomial for the reduction. So this how for addition we are doing the XOR operation, whereas for multiplication, the multiplied polynomials we are reducing by taking an irreducible polynomial. This way we are going to get the results. So this is the concepts we are applying for the construction of the next table. Let us discuss about, this is for the addition. The first one, table is representing for the addition. The second one is, it is representing for the multiplication. How addition will be performed, and here you can note down here how these elements are represented here, because this is, we are doing it for a Galois field of 2 to the power of 3. 2 is our the p value, and n is equal to 3. 2 to the power of 3 means we are having 8 combinations. We start with 000 and we are ending with 111. Similarly, along the row wise, 000 to 111. What are the 8 different polynomials we are getting? So this is 000 means it is 0. 001 means it is 1 because x to the power of 0. Then 010 means it is x. Then 011 means x plus 1. The weights you can keep on multiplying here. 100, it means x square. 101 means it is x square plus 1. 110 means it is x square plus x. And 111 means it is x square plus x plus 1. Similarly, along the row wise, we are finding here 000 means 0, 001 means it is 1, 010 means it is x, 011 means it is x plus 1, 100 means it is x square, 101 means it is x square plus 1, 110 means x square plus x, and finally x square plus x plus 1. Now you simply perform the XOR operation between these two values. what we get for that? 0 is XORed with any value here. We get the same values 0, 1, 1, then next as x plus 1, x square plus 1, x square plus x, then x square plus x plus 1. Let us do the last one now. Intermediate you can do it. I will go with the last one now. This one with this rows, all the column values. X square plus x plus 1 is XORed with 0. We are getting the x square plus x plus 1 only. Then x square plus x plus 1 is XORed with this 1 here. This XORed with 1. What we get here? So when I XOR 111 XORed with 001, the 1 will be cancels and we left with 110. 110 means x square plus x. So that's how I got this. The next one is x square plus x plus 1 is XORed with x. When I XOR x square plus x plus 1 with x, then the xx value will be, the xx value will be get cancels and we left with x square plus 1. So that's how I got this. Then next one is x square plus x plus 1 is XORed with x plus 1. It is XORed with x plus 1. When I XOR that values, I left with my x square value. So that is what I'm getting here. The next one is x square plus x plus 1 is XORed with x square. It is XORed with x square. So then I left with x plus 1 answer. I left with the x plus 1. Then x square plus 1 is XORed with x square plus x plus 1. Then what will be cancels? X square and 1 will be cancels and we left with x. And finally x square plus x plus 1 is XORed with x square plus x. So there x square and x will be cancels and we are left with 1. And finally x square plus x plus 1 and x square plus x plus 1 both will be cancels and we are having the result of that is 0. So that's how the addition, the polynomial addition will be carried out in this fashion. Let us discuss about how multiplication takes place. The multiplication, we do the multiplication, later we are reducing. How we are reducing that? By considering an irreducible polynomial, what it is given here. For a given irreducible polynomial, x raised to cube plus x plus 1. By considering this irreducible polynomial, we are reducing our multiplied polynomials. So I take one example and I want to elaborate about that. Let us move to this now. What is that? X square into x square. X square into x square is how much? X square into x square means we are going to get the answer for that is x4. X square into x square means x4. What is my highest degree of my polynomial here? Irreducible polynomial. It is cube is there. So therefore, how I can write this x4 now? The x4 I can split this power as x into x cube. X into x cube I can write it. When I write x into x cube, and what is the result I get here? X cube equal to what I get here? X cube equal to x plus 1. So substitute the value of that now. X of x plus 1. I got this x plus 1 from the irreducible polynomial. I simplified the irreducible polynomial for x cube. So then I get this x plus 1 and that's value I'm substituting for this x cube. Now multiply x of x plus 1 here. What we get now? X of x plus 1 we are getting as x square plus x. x square plus x is there here. So that's where we are getting it. Similarly, I'll take one more example and the other part I'll leave with you. Yeah, let us move to another one. Yeah, this one I'll do it. This I multiply with this. X square plus x plus 1 I'm multiplying with x square plus x. When I multiply that, what is the answer we are getting here? We are getting the answer for that as first x4 we get it. Then I am getting as x cube. Then I am getting the answer for that as x cube. Then I am getting the answer for that as x square. Then I am getting the answer as x square plus x cube. X is now multiplied with this x square plus x plus 1. I am getting as x cube plus x square plus x. Now simplify here. So after doing the XOR, what you left with now? X cube will be cancels. X square will be cancels. And we left with x4 and x. x4 and x we left with. So just now we computed what is x4 here. X4 means it is x square plus x plus 1. I substitute that value in this equation now. In this equation I substitute that. X4 means it is x square plus x. This is x4 value. Now plus we left with here even this x value we left with here in this x value. I'll take that now. Now again I am doing the performing that XOR operation. This and this will be get cancels and we left with x square value. So that's where we are getting the x square. When I multiply x square plus x plus 1 and with this x square plus x, I am going to get the answer for that as x square. So this how this table can be constructed. After multiplying the two polynomials and we need to reduce it if our degree is crossing, then crossing above the order of 2 here, the degree is crossing over the 2 degree, then we are reducing the degree of that polynomial but considering this irreducible polynomial and irreducible polynomial. So this how we are computing the multiplication. Now in the same example, considering this the previous example, I want to represent that in the integers. If I take the value of x equal to 2 and whatever we computed in the previous tables, if I substitute that in that x as 2, then I am going to get this kind of addition table. Here the 1 is there, here it is x is there because x equal to 2 I am getting, and this value will be x plus 1 is there, so that's why 2 plus 1 equal to 3, and this will be what I'm having here, x square. This will be x square. No, I think it's not x square, it is let me calculate this. Yeah, it is x square. It is x square is there. X square means it is 2 square will be 4. Then this will be 5 means the x square plus 1 is there. So 2 square means 4, 4 plus 1. That's why I am going to get this table, the addition table for that. Similarly, whatever the table we computed for x square plus x, and this what I got there, x square I got there. For x square means x is I am substituting as 2, then I am going to get the value for that as 2 square will be 4. So that's why when I consider that x equal to 2, so finally I am getting the table for addition and multiplications for over the Galois field of 2 to the power of 3. We are getting like this. And now additive and multiplicative inverses, how we are computing that. Whenever I add any element with another element, I supposed to get an additive identity element. By adding 0 plus 0, I get a 0. So that's how I say that for 0th element, the 0 will be my additive inverse. Then for adding 1, what value? By adding to this 1, by which value we are getting this identity element? By adding 1. So therefore, the additive inverse for 1 will be 1 is there. For 2, by adding 2 value to this 2, we are going to get the identity element. For therefore, for second element, the additive inverse will be 2. So like that, for 7th, now by adding what value we are getting this identity element? By adding this 7 value. So therefore, the additive value for 7, the additive inverse will be 7 is there. So that's how we get this, the additive inverse. We are computing that way. Next comes multiplication, multiplicative inverse. How we are finding the multiplicative inverse? Wherever we are finding a multiplicative identity element is there, that is this one, this one, this, wherever we are having a multiplication identity element, by multiplying 1, this one with 1, we get the identity element as 1. So therefore, for multiplication for this element 1, the additive multiplicative inverse will be 1 is there. For 0, nothing is there. For 0, we don't have any multiplicative inverse because we are not finding any identity element of the multiplication under this row here. So therefore, we don't have any multiplicative inverse for that. So coming to this 3 now. For 3, with this 3 multiplying what number, we get this one by multiplying this 6. So therefore, for 3, the multiplicative inverse will be 6 is there. And for 7 now, multiplying what number, we are getting this identity element by multiplying 4 with this. By multiplying 4 with this, we are getting the identity element as 1. So therefore, for 7, the multiplicative inverse is 4 is there. So this how we are computing the multiplicative inverse and as well as additive inverse. The same thing, it is elaborated much more in the next slide. That is finding the additive inverse. Finding the additive inverse. We are finding the additive inverse for the Galois field of 2 to the power of n. The same way how we did in the last slide, that's why we are constructing this table and we are finding the zeros along the diagonal here, and these are our additive inverse. For 0, the additive inverse is 0. For 1, the additive inverse is 1. So that's how I get this additive inverse table. For multiplication, finding the multiplicative inverse, how we are getting that? The same way how I mentioned you to construct this table here. So multiply these polynomials with the column polynomial. The order of the polynomial will be, the degree of the polynomial will be shoots up. To reduce that degree, we are taking the help of irreducible polynomial. By taking the irreducible polynomial, the degree of that polynomial we are reducing it. So that's how we get this table, and now you can identify wherever we are getting ones here. We are getting the ones at this place, that is additive identity, multiplicative identity element. This is the multiplicative identity element. This one, this one, this one, this one, and this one, and their corresponding elements, that is 101, that is 101 means 5. This is 5. For this 5, the multiplicative inverse will be 0 1 0. 0 1 0 means it is 2. For 5, the multiplicative inverse is 2 is there. For 6, the multiplicative inverse will be 3 is there. So that's how we are finding out the multiplicative inverse for the Galois field of 2 to the power of n. More generally, the extended Euclidean algorithm can be used to find a multiplicative inverse in 2 to the power of n for any n values, can be done with this tabular method, or else we can also use the extended Euclidean algorithm to compute the same multiplicative inverse. And this extended Euclidean algorithm I already discussed in the lecture series 4 here. So you can refer that how this extended Euclidean algorithm is used to compute this multiplicative inverse for that. The summary and additional links. We are learned in this lecture how to generate the finite fields of the form Galois field of 2 to the power of n, the modular polynomial arithmetic, and finding the multiplicative inverse with a tabular method, and as well as the an algorithm, that is extended Euclidean algorithm. For additional reference, you can make use of that our the textbook, that is William Starling's 6th edition, and you can visit the YouTube links to get some more additional information on that. With this information, so thank you very much for pleasant listening. Thank you one and all.